The first example we're going to see is the most simple example of the use of abstract propositions. We're going to enter a logical structure that is abstract, and then we'll use that abstract structure in a specific concrete scenario. As explained before in the introduction, this abstract part is materialized by abstract propositions, or APs. They have this form here, meaning the variable part is this format. It is necessary for the system to know what is distinguish the fixed content from the variable content, and also to allow it to assign a value, the adequate values to these variables here. For now, the point is that this is a tool that the system can use, and the way the system uses these tools, these abstract tools or structures, is by translating them to concrete versions, concrete data, in which then it uses on the fly as any other non-abstract proposition. The values of these variables will be determined by the non-abstract propositions, or NPAs. Depending on the NPA that is related to this PA, it will determine its values. The values will be determined. These values can also be changed by self-mapping. We're going to get into that after this example. For now, this is just a simple abstract proposition. And the other one, and you can see that it's a very simple example, and we're going to now enter. This is the non-abstract propositions, meaning the concrete data that the system is going to learn. And now we have these four propositions here. The difference in this model relative to the previous version is that now we have two types of data structures. In the previous model, we only have these kind of propositions, which meant there was only hard coded data, and hard-coded logical relationships. But now we also have abstract structures, which can be used in the same way and applied by the system to solve concrete problems. So I'm going to see the most simple example of that. Now I'm going to ask if we can infer that N is a child of Peter based on the fact that Peter is parent of N. For us, this is very straightforward, but the system just learned that, and the point is that the system learned that this is a logical relationship because of that abstract structure. The difference in the previous version, I would explicitly create this logical implication from this left side to this right side here. In this version, it learned an abstract version of that application. I entered an abstract version, a general rule, which the system will now use applied to this specific example. As you see, and the interpretation that I'm going to make of this reasoning is the same as the next examples that will follow. So this is it's important to start from there. As you see, this means that we started with this P2 here. P2 is the left hand side, and P3, I think it's P3, is the right hand side. We started from here, from P2, and we ended with P3. the logical path that it follows is generalized P2 to P0. This means that P0 is an instantiation of this proposition here. P2 is an instantiation of this proposition here, and of course P2 is an instantiation of this abstract proposition here. This one, this is instantiated in this case, but of course in this case it was not an instantiation, it was an abstraction, because the system went from here to here, and from here it's now working in the abstract logical structure, which then it's specialized to P3 again. So again, as a conclusion, that is. So this means that this reason here, and this is a new feature in this version, that the reasoning, this time the system performed an abstract reasoning. It took the hard data that you gave it as assumptions, it abstracted that to a known abstract structure, which then it used to do the logical computing, and it arrived. As soon as it arrived at a positive result, it gives us the answer. So this is what it means in this specific case. This is the most simple use we can make of abstract propositions without any further properties being set, namely the variable mappings, which I will tell you about in the next example. Now, for this second example, we'll be using the same scenario as before, but this is a different approach. In this approach, we'll demonstrate the first use case demonstrated abstract reasoning, and the second case will demonstrate the generalization of learning, meaning that you will give the system a specific R data. It will create an abstraction from that, and it will use that abstraction to then give you further results. And it will apply this abstraction to new situations based on that abstraction that it performed. So I'm going to introduce first piece of data. Second fact that I'm going to add is this one. And what's happened is that if you go here, if we now go here, going to tell the system that a specific instance, and this is the same way as the previous model, we just providing it a specific instance of a logical implication between this fact on the left hand side and the one on the right hand side. The difference here is that instead of storing this hard data, the system will create an abstract form of this implication using abstract propositions, and that's the way it is going to be represented here. And this will allow the system to apply that abstraction to a different data that it is provided. So we're going to add, we could do an equivalence, but we're going to do just an implication for the sake of example. So what you can see now is that the system added these two abstract propositions. As I just said, the way, unlike the previous version, now it generalized this learning to a more abstract form, and the advantage of it is that next I can ask him about a similar thing, although with different data, and it will be able to give me an answer based on that general logical structure. So it generalized the first piece of information I learned to answer the second one I'm going to ask it about without me previously having explicitly given it answer. I'm waiting the two new pieces of data, and as you can expect, the next thing I'm going to do is ask it about this new data. Now I'm asking the system if it can infer this result based on the right hand side, based on the assumption on the left hand side, and it should give me a positive answer using a logical, abstract logical structure, because it learned and generalized from the previous example that I gave it. The first data was about Peter and Anna, but now I'm asking it about Alfred and Tom. So it's able to generalize the initial learning to answer to this case too. And you see that it's what it is. I already explained to you how to interpret this. It's exactly the same interpretation as the previous scenario that I demonstrated. The difference here is that I didn't tell the system that anything about Tom and Alfred specifically, but it was able to arrive at this conclusion because it generalized the information it learned from Peter and Anna. Okay, the generalization happens thanks to these new types of data structure, which are these new types of propositions. So as you can see, this demonstrates not only abstract reasoning, but generalization of learning. This third scenario, I'm going to show you how the system creates a linear strategy to solve a problem. And it is a linear in the sense that we're going to give it one initial state, one end state. We're going to give it a tool, a single tool. This will be the next scenario will complicate this a little bit more with more tools, but for this scenario we're just going to use one tool. The system only knows how to do one thing. And we're going to ask the system how it can use that tool, if it can use that tool to arrive at a given state, starting with another state that we're going to give it. To use a different example, it really doesn't mean anything. The system has no idea what this is. This means nothing for the system, because it just follows logical rules, whatever the statements actually mean. But I gave it this form for us to show you an application, different application of this. So suppose that you have 4 objects. There can be 4 blocks on a table, for example. And the only thing that the system is going to learn how to do is to place one block on top above the other, right above the other, and switch the other 2 positions. That's all. Okay. That's all the system will be able to do. And I'm going to add this here. This is a permutation, as explained in the introduction. This is similar to the mathematical notation of a permutation, but it just means that this is a sequence of numbers. Each number is a variable here, and the actual sequence tells you how we map the variables in a single step in the reasoning. Meaning that if you, in this case, it's self-map, meaning this rule is applied, this proposition applied to itself. So this means basically these numbers mean that if you start this proposition with the block 1 here, 2 here, 3 here, and 4 here, the next, if you apply this rule to itself, the next state that it will provide is that block 2 will be in place of 1, block 4 will be in place of 2, 1 and 3 and 3 in the place of 4. That's what this means. This is for those who are familiar with mathematics, this is a permutation. As explained, this self-mapping can be any function. For the sake of this proof of concept, I'm using what possibly is the most simple one, which is a permutation. But in general, this can be any function with one or two requirements or restrictions. First one is that it cannot be the identity, because if it were, the system would generate a reasoning, a tautological reasoning, meaning A implies A, and that doesn't change anything, so there's no point in using that rule. Actually, that rule, if you want to know, it's the identity permutation, which is 1, 2, 3, 4, and so on. If we had more variables, of course, you can have many more variables as much as you wish. This is the identity permutation. This is one restriction. It cannot be the identity permutation, meaning that it has to change something new has to happen. And the other restriction is that it has to be bijective, meaning that it has to be an invertible transformation. Or, put it in another way, you cannot have two states arriving at the two different states, initial states arriving by means of the transformation to the same end state. And this is very important because the way the system works, it needs to be able to look at it both ways, starting from the start assumptions or from the end result. And if you don't have an invertible transformation here, it will just not work. I mean, it can work, but it will be a reasoning that makes no sense at all. Because what happens, and you can understand intuitively, you can understand that the system has to follow the rules of logic. So everything has to be determined by rule logic. It means that you cannot leave room for decision by the system. So regardless of what state the system is looking at, it has to know what will be a possible consequence of it, and there can be more than one consequence, but the originator of that state can only be one. Okay. Let's go. This is a general idea. So this is the only tool that the system will learn. So besides, of course, the other two pieces of information that I need, which are the initial state and the end state. The initial state will be, this is pretty much arbitrary, but I picked this one. I'll show you more visually what this means, but it really doesn't matter much. Pretty much arbitrary. So the system now. So we now have this piece of information, this tool, and these two pieces of information. What we're going to ask is, we'll start with this state, and we'll ask the system if it can arrive at this state using the only tool that it knows, which is this one. The system will apply the tool to it because it's the only tool. It can only apply the tool to itself and hopefully reach the conclusion. And as soon as it does that, it will give you the reasoning. This is very straightforward in the sense that you don't have one tool, but if you have more than one start assumption or more than one conclusion or more than one abstract tool, as you understand, it would get very complicated very quickly. But the system handles that in the most efficient one. You only would risk, if you complicate the scenario, you can only risk waiting a bit more time. But as you will see, this is still a very efficient system. This is a simple setting, and now I'm going to just illustrate what this can mean. It doesn't really matter for the machine, it doesn't know what this is, but for the sake of us interpreting this. Suppose you have 4 blocks on a table, for example, and you want to arrive at this. You want to have an initial state, which is this one, applying the left-hand side transformation to this initial state, which is placing 1 above 2 and switching the other 2. So you are starting with this configuration of blocks. and you want to, in order to know if the rules that you give the system with the tools that it has, it can arrive at something like this. I think it's this. We'll see. Should be something like this. So if there is a path, the application will tell us what that is. Again, it can only give you an answer using abstract reasoning for the same reasons that I explained before. And that's exactly what happened here. If you look at, we started with P1 and we ended with P2, and from bottom up it followed this chain of logical implications, and all these three middle steps were all using instantiations of this abstract proposition here. Okay, and you can see, looking the reference at the left hand side, you can see what value, what was the specific instance of this abstract proposition. So basically that's it. This means that you have a transformation. If you want to visualize this, it means something like from P1 you want to P0. P0 is the same as P1. It's just an instantiation of the P1 is the non-abstract proposition, and P0 is the instantiation of the abstract proposition. Secondly, it went from P0 to P01. P01 tells you that it did something like placing 3 above 1, and then switching 4 with 2. So it's something like this. You see the next thing, and so on. And you can follow the example by yourself if you want to check it out, and you'll see that you arrive at something like this. I'm not sure if it was 1, 3 or 2, 1. It doesn't matter, but it was each of these intermediate steps in the reasoning can be represented as a change of configuration of these blocks. Okay, and yes, the system was able to apply the tool that it has to give you this result. So this demonstrates abstract reasoning, and the new thing here, which is it generated new data, or equivalently, it's based on the base geometry that it had, defined by the data that it learned, the initial hard data it learned. It generated new geometry in which it performed its work in the pretty much same way as it was doing the previous version, only with these non-abstract propositions. And another interesting thing to note here is that it generated from here to here, from P0 to P1, it generated new geometry, which is used. It then navigated on this new geometry to generate again new geometry. So this is important to point out, because this relates with the definition of a singularity system that I mentioned in the introduction. So this is just to make a bridge with what I explained initially to a concrete implementation of that in this system. On this last scenario, we're going to see system using more than one tool, more than one abstract tool, and applying more than one abstract tool to more than just a single pair of one initial state and one final state. We're going actually to give it 3 different tools, and we're going to start with 2 initial states, and we're going to try to arrive at a single end state. And we want the system to give us the most simple strategy to achieve that. And obviously, if you start with 2 states and you end up with 1 state, it's not a linear path anymore. This is just the most simple example of that, and we are going to use permutations for that. Permutations in the mathematical sense, operations that switch positions of different objects. And you can generalize this to pretty much any combination of this. We're going to use 5 variables and 3 abstract propositions, 2 initial states and 1 end state, but you can have any number of initial states, any number of end states, any number of abstract propositions with any number of variables in each one. It's up to you. So we're going to enter the 3 abstract tools that the system is going to learn. As I just said, these are permutations, meaning that the effect they have when they are used is just to switch. You can look at this as a sequence of numbers or blocks as before, and the only thing that the system will be able to do is to switch positions of these objects between themselves. Okay? You're going to, each abstract proposition is a way of the system to change those positions. It's given by this permutation here. It is a self-mapping necessary to create the new geometry, and basically what will happen is that the system will figure out the most simple combination of the 3 tools that it's going to learn to do the job. First one's already in. Now the second tool. Now the third tool. So this is a more complicated example than before. And of course, now we want to add the initial and the final states. This is one of the initial states. This is hard data or a non-abstract proposition. And now the end state that we want to get at, which is this one. So right now the system has these 3 concrete pieces of data and these 3 abstract tools. And the question the job we're asking you to do is to figure out how to go from here to here. It's not linear, and he has 3 tools instead of 1. So it means that if there is an answer, it will be a path in which the system uses this tool uses these 3 tools in a given sequence, and it can also use the same tool several times over consecutively. Okay. This is much better expressed in mathematical notation, and I'm going to show you why it's easier to look at it that way. But you'll see what this means. Let's look at the results. As you see, it's pretty quick. We give you the results. It generated all these geometric units here, which weren't in the system. The only thing that was in the system was these 6 propositions. But it generated new geometry as before. It navigated that geometry to give you reasoning. So what happens is that you interpreted the right-hand side in the same way as before, usually from bottom up for some reason. We started. I know that we started because I know this example, and we started with P4 and P3. Sorry, P4 and P3 here on the right-hand side, and we arrived at P5 here on the top. And what happened if you follow the sequence of the chain of reasoning here, you see that from P4 it generalized to this one, P0666, but from here on it navigated on an abstract geometric structure that was generated on the fly. And from here it went on until, and it did the same thing from P3 onwards, and because there is only one end state at some point in time, because there is only one end state, and because we always want the system to give us the most simple answer, it logically follows that at some point these 2 logical sub-chains of reasoning should have converged to a single point. And let's try to see what that was. It should be a duplicate on the right hand side here. it's this P073. If you look P073, there were two different propositions arriving at the same conclusion. Each of those started from one of these initial assumptions. Okay. From P073, it went on to P5 right away. This is how it is. So this demonstrates, this final example demonstrates abstract reasoning and the use of different tools to create a geometry, a new geometry on the fly, dynamic, logic, which it then uses to give you the result. Now, what we can, I can show you the advantage of using, especially this in mathematical notation, because in the right-hand side you are looking, all of these are instances are either non-abstract propositions or instances of abstract propositions, and it doesn't, it's not very obvious which abstract proposition is which. But if you look at the left-hand side and you study this response, you can do that if you want. You should conclude that what happened is that we started with this initial proposition, let's call it PNA3, and this one, and we arrived at this conclusion on the left-hand side. In the mathematical terms, what this means is that the conclusion that we arrive at can be expressed as a factorization or a product or a composition or whatever you want to call it. These are all the same thing in mathematical jargon, of these different factors, which are powers of each of those tools, the three tools that is there. For example, if you have the sequence, means that it applied PA0 first, this tool first, and then it applied this tool on the result of the previous one. And the exponent means that it applied this tool 2 times consecutively. This is what it means. This is usual mathematical notation for compositional functions, in this case the function being a permutation. Okay, this is useful because it tells you, it tells you how you can clearly see how the system used each different tool. Okay, these are all different tools that it used. Okay, 1, 0, and 2 in this case, and one used them more than one way at different points. So this is pretty much it, and this is the end of this demonstration. And everything that was explained in the introduction is already demonstrated here. Thank you very much.